We're supposed to talk about syzygies today. Give a very basic introduction to those who may not have seen so much of this. So R, and even for the experts, you might see some points of view. So R is a polynomial ring in n variables over a field. And then we're looking at a linear map. So the image of a linear map into R from RS is called an ideal. So linear means R linear, and as is convention in Macaulay 2, the arrows go from the right to the left, right? So if I write down a map from the free module R to the S into R, I'm going to write the arrow to the left so that the matrices go the right way. So this is represented by a 1 by S matrix. Okay? So a linear map given by a 1 by S matrix is called an ideal. Now we have the image, so we can also look at the kernel. So the kernel of this ideal is its syzygy module. Syzygy module. Right, so whenever you have a linear map and you know the image, you should ask for the kernel. That's the syzygy module. Now, of course, this itself is finally generated, so it's the image of another linear map. Right? So maybe this kernel has T generators. Right? So we have S generators for the ideal. Now if the kernel has T generators, we can write it as the column span of an S by T matrix. And so on. Right? Then we say, what's the kernel of this map? Well, maybe it has U generators. And we keep going. Okay? So these are the syzygies. So the first syzygies, the second syzygies, and so on. Now in this fashion, we get a free resolution. And in the settings that we're discussing here, we will do this in a minimal way. So we're not going to be wasteful at all, right? We are conserving resources such as chalk. And so to conserve resources, we will try to get away with small numbers, ST and so on, as small as possible. So we're going to do a minimal free resolution, and it looks like this. Right? So at the left, we have an R, then we have an RS, then we have an RT, and so on. RU, blah, 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 blah. Okay? So this is given by a linear map given by a 1 by S matrix, an S by T, a T by U. So the indices go the right way. Now, when we do this in a computer, for example, in Macaulay 2, there's a built-in command. All we're going to do is we're going to say res I, and it will produce something like this. So if I is an ideal in a polynomial ring, we're going to say res I, and we get a sequence of maps like this, and we can and should ask for the matrices in this map. Okay? Now, since we're in a polynomial ring over a field, we're done. After at most n steps. Okay, that's the famous Syzygy theorem. So this was proved by David Hilbert 125 years ago. Exactly 125 years ago, Hilbert proved in his famous paper that we're done after at most n steps. Very important theorem, nowadays proved using Grobner bases in a course. And what we need to understand is why did Hilbert? I will try to explain. That's the statement. But when you look at a mathematical theorem, you should always ask, why was this proven at the time? Why was Hilbert interested in this over a century ago? Why did he prove this theorem? Okay, very important question. We're done after at most steps, but we also have a lower bound on the number of steps. We need at least codim of I many steps. Right, so by codim of I mean the codimension of the variety. So I defines an affine variety in n-dimensional space. That dimension is either 0, 1, 2, 3, 4, 5 up to n, right? And n minus the dimension, the codimension, that's always a lower bound on the number of steps we need, right? So we're always between the codimension and n in the number of steps we mean. Now if in this inequality, so if in this inequality to the codimension, if equality holds, then we say the ideal is Cohen-Macaulay. Okay? So these are names of two people. There were two people. There was Cohen, a little later, and Macaulay, and he was earlier. And we're going to say an ideal or corresponding ring or variety is Cohen-Macaulay if the resolution is as short as is permitted by the lower bound. If the resolution has codimension I many steps. Okay? So I'm going to go through some examples this morning. Here's my example 1. Okay? So why did Hilbert do this? Hilbert was interested in counting. Okay? He wanted to organize the principle of inclusion-exclusion. So when we teach discrete math to undergraduates, we teach inclusion-exclusion, and that was what Hilbert was interested in. He wanted to organize counting, and he wanted to organize inclusion-exclusion. So let's ask a kindergarten question. How many boxes are in a 2 by 3 by 6 grid? Okay, so you have a child has some cubes, right? They play with little cubes, and they put cubes together to make a big, brick, right? And it's a brick of length 2 by 3 by 6. How many little blocks does the child use? Okay? Well, the answer is 36, right? So we know a method called multiplication that finds the answer, but I'm going to give you a more complicated answer. I'm going to derive the number 36 for you, okay, in the will that makes sense for Hilbert. So first of all, let's talk about the grid. Okay, so the grid is given by an ideal generated by 3 monomials, x squared, y cubed, and z to the 6th. So we're now in a polynomial ring and n equals 3 variables, and I will call them x, y, z rather than x1, x2, x3. So whenever I'm in a 3 variable situation, I'm going to use the letters x, y, and z. Now, okay, so now we have a map, right? So this defines a map. So you should think about this as a 1 by 3 matrix, right? So this I is a 1 by 3 matrix, so it defines a map from R to R3. The image is the ideal, and according to what's on the left side of the board, we should ask the question, what is the kernel of this map? What's the kernel of a 1 by 3 map? Okay? How many generators, Chao-Chan, do you think the kernel, this 1 by 3 matrix, has? It's a 1 by 3 matrix. How many generators does the kernel have? To make this interactive. How many generators do you think? It's a non-zero matrix of format 1 by 3. How many generators in the kernel? 2? What do you think? The question clear? We have a 1 by 3 matrix with non-zero entries. How many elements do you need to generate the kernel? You say 3, you say 2. You say 3? 2. Okay. So there's a conflict. So she says 2, you say 3. Okay? Okay. Well, let's see how this goes. Okay. So here is our map, right? So here is R. Then here we have this 1 by 3 matrix. And the answer is actually 3. Draw this a little more. So over the polynomial ring, you actually need 3 generators. Over a field in a linear algebra class over a field that you take in your undergraduate class, you need 2. But R is not a field. R is not a field. R is a polynomial ring. You must never ever use field undergraduate linear algebra when you, you should use it also, keep it in mind, it's useful. But this is not a field, okay? So we have this linear map I, and then the kernel in this example requires 3 generators. So the first generator is the column vector y cubed minus x squared 0, okay? So this vector times that vector is 0, right? And then there are 2 more. There's minus z to the 6th, 0, x squared, and then there's 0, z to the 6th, and y cubed. And trust me, I claim, okay, now you have to trust me. So certainly these things are in the kernel. They are independent. None of them can be written as a polynomial linear combination of the others. And I claim they generate everything. So if you come up with any other vector in the kernel, I can write your vector as a polynomial linear combination of my columns, okay? But now these things are not independent. It turns out that these 3 column vectors are linearly dependent, and there's one more relation, namely the relation z to the 6th y cubed x squared, and you can see that z squared, z to the 6th times the first column plus y cubed times the second column plus x squared times the third column is 0. So this is in the kernel, and again this generates the kernel. So in this example, you can see that the last 3×1 matrix is essentially the original 1×3 matrix with the order reversed in this example. Okay? Now another thing that's very, very important when using matrices in these kind of settings is to give names to the rows and the columns. Okay? And I'm going to name the rows and the columns according to the degree of this object. So for example, the original generators have degree 2, 3, and 6. So in red I'm just writing the degree of these elements. Okay? Now of course I'm multiplying this row vector against this matrix. So this one inherits, the rows inherit the names from the previous matrix to the left. Right? So the name, of this row is 2, 3, 6. That comes from the generators. But now I have to name the columns, right? So the name of this column is 5 because these column vectors are homogeneous of degree 5, right? I have y cubed times a basis vector who is already in degree 2. That makes 5, right? So the degree of this column is 8 and the degree of this column is 9. Right? So every row and every column has a coherent red degree. And Macaulay knows about the degree, and you should know about that degree. Okay? So in this game, whenever you have a matrix with polynomial entries, there are rows. The rows and columns of your matrices have names, and they're typically the degrees. So even the last one here, so now this inherits, the degree 5, 8, 9. What goes here? We'll say it's early morning. What's the degree of this column? 11, right? Because 5 plus 6 is 11, 8 plus 3 is 11, and 9 plus 2 is 11. Okay? So we've constructed a minimal free resolution. What this means is that homology is 0 everywhere except at one place. So here there's no homology. That means the image of this map is precisely the kernel of the next one. Okay? So if we have 2 linear maps, one after the other, okay, I'm going to say the sequence is exact if the previous map, the image of the previous map is in the kernel of the next map. Then it's exact. But, well, the kernel mod the image could be non-zero. That's called homology, right? But if homology is 0, if the kernel exactly fits the image, then that's fine, right? So we have no homology here, no homology here, no homology here. By convention, we do have homology there. Right? So here, so by convention, and this is a convention. So the homology here is simply the coordinate ring. Right? So what is the homology here? Well, it's the kernel mod the image. Well, the kernel of this is R. Right? If R goes to 0, the kernel is R. What's the image? The image is the ideal. That's how we define the ideal. Right? So homology is R mod I. Okay? So when we speak about the resolution of R mod I, we're building an exact sequence of R modules, free R modules, it's exact everywhere except at the leftmost place. The homology is the ring we're interested in, R mod I. And the ring we're interested in is the pile of cubes that your kindergarten child was playing with 5 minutes ago. That's R mod I. Okay? So now let's do the counting. Right? So the counting is done by the Hilbert series, named after the same Hilbert for the same reason. Right? So the Hilbert series is done. So we think about this sequence as a process of inclusion, exclusion. So, well, first of all, let's write down the generating function for R. Right? So this is the Hilbert series of R as a graded vector space. Right? So R, this is the number. Right? If you expand this series, then the coefficient of t to the n is the number of monomials of degree n in 3 variables. Right? So this object represents R. Right? Now, but since the sequence is exact, right, at each step the kernel matches the image. So we can just, go like this. Okay? So let's just record, the degrees. Right? So what are the degrees? So we have 1. So this is 0. Right? So the degree here is 0. So we just take the alternating sum of all the red numbers. Right? So as a generating function. So it's 1 minus t squared minus t cubed minus t to the 5th. Right? So the t to the 0 is here, and then minus t squared minus t cubed minus t to the 6th, and then plus, this is 6th, plus t to the 5th, plus t to the 8th, plus t to the 9th, and then minus t to the 11th. Okay? That's it. That's the Hilbert series. Now, in this particular example, this actually factors, and this is just a polynomial. So this is 1 plus 3t plus 5t squared plus 6t cubed plus 6t to the 4th plus 6t to the 5th, almost done, 5t to the 6th, plus 3t to the 7th, and finally t to the 8th. Okay? And that's your number 36. Right? This enumerates the 36 blocks of your child according to degree. Right? So those are the monomials not in the ideal. 1, x, y, z. xy, y squared, z squared, xz, yz, z squared, blah, 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 blah. Right? So the monomials not in the ideal are the blocks that the child was playing with. There are 36 blocks, and this is the generating function. And this is the reason why Hilbert wanted to have the Hilbert series. Okay? He wanted to carry out inclusion, exclusion. Why, we can further ask, did Hilbert want to carry out inclusion, exclusion? Because he was interested in the hottest topic in mathematics at the time, called invariant theory. Right? He wanted to count invariants. So invariants are geometric quantities, such as the discriminant, that measure important things about points, curves, surfaces, and so on. So the succession here was there was invariant theory to count the number of invariants for a certain problem. Hilbert introduced the concept of ideals and modules, and then he realized that he had this generating function. But in order to show that this generating function actually can be computed as a rational function, he needed this theorem. So therefore he proved this theorem. Okay? So that's it. That's how it went historically. Okay, this ring is Cohn-Macaulay, right? So let's record that the codimension of I is 3. Another word that I like to throw at you. So there's a distinguished element in degree 8 that's called the socle, right? So there's exactly one far out box, right? The socle element is x y squared z to the 5th, right? This is the largest brick that's not in the ideal. That's called the socle. Okay? There's one element in the socle. So the codimension is 3. So ideal I is called Cohn-Macaulay. Right? Because the number of steps in the resolution is 1, 2, 3. That matches the codimension. So in this case, of course, we knew this has to be the case, right? Because n is 3 and codimension is 3, so it has to be Cohn-Macaulay. But moreover, it's also what's called Gornstein. Okay, this is Danny Gornstein. Danny Gornstein was a group theorist, a very wonderful guy, a very open-minded person, but he was mostly a group theorist. He was interested in other algebra as well. And later in his life, he was the director of DIMAX. So DIMAX was an NSF-funded institute, like MSRI, SAMC, and so on, IMA. And just like IMA, it disappeared. But it wasn't Gornstein's fault. But one thing Gornstein never understood is what is a Gornstein ring. Right? So somebody named, early on, when he was very young, he wrote a paper on rings, right, and talked about some property. And then many, many years later, somebody called something a Gornstein ring. And one person who never understood what a Gornstein ring is Denny Gornstein. Unfortunately, he passed away in the meantime. So Gornstein means the socle is one-dimensional. And that's equivalent to saying that there's sort of a self-symmetry. You can see, right, the cube, there's an obvious self-symmetry. For example, here, 1, 3, 3, 1. And that's one of those facts, right? If you are in a Cohn-Macaulay situation and you have a 1 here, then these numbers are automatically symmetric. That's called Gornstein. Another way to see the Gornstein property is you can write the ideal actually as the perp of x y squared z to the 5th. So if you look at the ideal, the left ideal of all differential operators, something that Japanese statisticians are very interested in, the holonomic system that annihilates this function, right? This turns out to be generated by linear differential operators with constant coefficients, namely ddx squared, ddy cubed, and ddz to the 6th. Okay? That's equivalent. So Gornstein ideal, at least in the Artinian case, is one that annihilates a given homogeneous polynomial. Okay, now there are other reasons why we would be interested in these kind of generating functions. So since I already mentioned algebraic statistics, there's something called reliability theory. That's a very nice story. So let's say we have a graph that's connected somehow like this. So this is the power grid of Korea. So these are, electrical stations and there are connections between them. Okay, maybe it's a planar graph, right? That's the Korean power grid. But on a very, very hot day in the summer, there's a probability that some of these connections might fail. Right? So today, this connection fails. And maybe this. Right? And we're very interested in the probability that the network stays connected. So there's a failure probability on each edge, t, or maybe t1, t2 for different edges. And you want to calculate, the probability that the network stays connected, that you can still, have the power grid going. And that's a problem like this. It's very much modeled like that, and you get the reliability polynomial. So this is one topic that Henry Wynne has started, but I think the champion in this right now is Fatemeh Mohammadi, who has really perfected the art of using syzygies in algebraic statistics by way of reliability theory. It also ties in with chip firing on graphs and topics that discrete math people are very interested in. Okay, example 2. Let's do another example. Any questions about my first example? Okay, here's example 2. Let's increase the number of variables to 6. Okay? And I'm going to call my variables x1, x2, x3, and y1, y2, y3. And the relations I'm going to write down are x1, y2 minus x2, y1, x1, y3 minus x3, y1, and you can guess the last one, right? So x2, y3 minus x3, y2. Okay, so these are the 2 by 2 minors of a 2 by 3 matrix, but I don't tell you that. Okay, so who do you look puzzled? x1 times y2 minus x2, y1, x1, y3 minus x3, y1, x2, y3 minus x3, y2. That's my ideal. Okay, so I've given you a 1 by 3 matrix that maps R3 into R, and the image is this ideal. Okay, so okay. So now you're too lazy to do the resolution by hand, so you go to Macaulay 2 and you say resolution of this ideal. And here's what Macaulay 2 gives you back. Okay, so Macaulay 2 says 0, R, and here you always have I, R3, and then Macaulay 2 says this is it. Now there are only 2 linearly independent syzygies. So here we had 3 generators, but we required 3 generators. But in this example, there are only 2. Okay, so there's some mysterious 3 by 2 matrix. That's it. That generates the kernel freely. Okay. Now, what is this mysterious matrix? Well, at this stage, you ask Macaulay 2 to show you this mysterious matrix, and you discover what's called Kramers Rule. So if you didn't know Kramers Rule of linear algebra, you will now discover it, right? Because the matrix that you see is x3, y3 minus x2 minus x2, y2, x1, y1. Right? So Macaulay 2 shows you this ideal. And of course, you know, this row vector times this matrix is the 0 vector of length 2. That's called Kramers Rule, right? Because the left kernel of this matrix is generated by the 2 by 2 minors swapped around, right? Those things are in the kernel and they generate the kernel. Is that clear? You guys look puzzled. Is that clear why these syzygies hold? Yeah. You multiply this row vector on the left against this and you get 0. Okay? Now, this one, by the way, is also Cohen-Macaulay, right? So the codimension I claim is 2, right? Because geometrically, this is really codimension 2 situation, right? So this is, you know, P1 times P2 in P5. I'm sorry, P2 times, what am I saying? P1 times P, yeah, this is the Segre embedding, so this is codimension 2, and so this is also now Cohen-Macaulay, because the length of the resolution is 1, 2. Okay, so our first 2 examples are Cohen-Macaulay ideals. Now let me modify this example a little bit. So I mentioned already that nowadays Hilbert's basis theorem is proved using Gröbner bases. So how do Gröbner bases interact, you might ask, with the resolution? Well, let's see how it goes. Let's look at the leading monomials here. x1, y2, x1, y3, x2, y3. And of course, I don't have to tell you this is the Markov basis, for the independence model. And so again, lots of motivations from statistics. Okay, now let's pass to the initial ideal. To the initial monomial ideal with respect to lexicographic order. So let's do that. So we go 0, R. Now the leftmost map given by the red monomials is x1, y2, x1, y3, x2, y3. Now what happens? In this example, it also happens that the kernel is given by a 2 by 3 matrix, by 3 by 2 matrix, but you get that matrix by zeroing out some of the entries here, right? The way the cancellation works, now some terms are missing, so you have to zero out some of the entries, and the correct matrix is 0, minus x2, x1, y3, minus y2, 0. Right? So the upper left entry and the lower right entry go away because they participated in the cancellation of terms that are no longer there. So that's a general principle. So general principle is that if things are nice enough, you can get from the resolution that you have to a resolution of the initial ideal, but rather the algorithm goes the opposite. Right? The way you build resolutions and the way Macaulay 2 builds resolutions, something called Schreier's method, that says at each stage we go the other way. Right? So we say, well, let's look at the leading terms here, and let's first calculate the syzygies on the leading terms. If we're lucky, we can now fill in the zeros. We can extend the syzygies to syzygies on the original step, and then we keep going. Okay? Now, this process is called S-pairs. So, Grobner bases, these are called the S-pairs. Right? So the S-pairs are the columns here that you see on the monomials, the syzygies on the monomials, they're called S-pairs. So Buchberger thought this was called subtraction pairs. Some people think it's called syzygy pairs. Some people think it's called Schreier pairs. I think of them as stingy pairs, right? Because it's the stingiest way of canceling the leading term. So S pair, the S can mean many things. It could mean subtraction. It could mean stingy. It could mean Schreier. Or it could mean syzygy. These are the S pairs. Okay, so that's my second example. Now really what Professor Quack is interested in is projective geometry. So let's do an example that has a bit more meaning in projective geometry. That's going to be example 3. Let's go back to n equals 3 variables called x, y, and z. And let's look at the ideal of 6 points in the plane. I happen to like 6 points in the plane, and Hyun-Suk Moon likes 7 points in the plane too, but we like 6 and 7 points in the plane. So let's talk a little bit about 6 points in the plane. So, for example, these points. Here are 6 points in the plane. Okay? So how would we write down the ideal of these 6 points in the plane? Okay? Now the first thing we always do, we always in this game, whenever possible, we work in projective space. So we write down homogeneous coordinates. So in yellow I have the homogeneous coordinates for these 6 points. So this is x, y, and z. So this is a picture in the yz plane. In the affine, this is the y z plane. So this is 1, 0, 0, 1, 2, 2, 1, 2, 1, 1, 3, 1, 1, 1, 0, and 1, 0, 2. Okay, so these are my 6 points in the plane, and my 6 points do not lie on a conic. Right? If I were unlucky, 6 points could lie on a conic, but my 6 points do not lie on a conic. Okay? Now, how do you write down the ideal? Well, what's the ideal of a point? Okay? The ideal of a point is generated by the 2 by 2 minors. Right? So if you want to speak about the point 1, 3, 1, we're interested in all homogeneous polynomials that vanish at this point. It's given by those, the 2 by 2 minors of this matrix. So in each case, I form the 2 by 2 minors of this matrix, just like here. I intersect these ideals, and then that's an intersection of 6 prime ideals. An intersection of prime ideals is called a radical ideal. And this homogeneous radical ideal is generated by cubics. For example, 2x squared z minus 3 z squared plus z cubed. Let me go give you one more. Gets more complicated. 8xyz minus y squared z minus 12 xz squared minus 3 yz squared z, and 2 more. And the other 2 are more complicated. Okay, so they're all together 4 homogeneous cubic polynomials that generates the homogeneous radical ideal of the 6 yellow given points. Okay. Now, what should we do with this? Okay, how can we see some structure? Well, first of all, let's observe that this ideal has codimension 2. Well, it's points in the plane, right? A point is 0-dimensional. A point in the plane has codimension 2. And it's also quite easy to see that this must be Cohn-Macaulay. Right? So if you have points in the plane and you write down the radical ideal of the points in the plane, that's automatically Cohn-Macaulay. So it's a Cohn-Macaulay ideal of codimension 2. Okay. Now there's a wonderful theorem. So every concept that I like you to remember, I'm going to write in yellow. So there's a very wonderful theorem called the Hilbert-Birch theorem. Same Hilbert, different Birch. Okay? And the Hilbert-Birch theorem says the following. I'm going to explain it to you in an example. The resolution looks like this. R, where here's my ideal. So my ideal is generated by 4 cubics, but it's Cohn-Macaulay, right? So therefore, I have to have only one more, right? The resolution, there's only one more module, and that rank here must be 3, right? Because the alternating sum of the ranks is always 0. 1 minus 3 plus 3 minus 1 is 0. 1 minus 3 plus is 0, right? That's inclusion, exclusion, right? The ranks, or speaking a bit more officially, if you do like undergraduate linear algebra over a field, and you should like it, if you do like undergraduate linear algebra over a field, you can tensor this with the residue field. You replace R by the field of fractions, right? Well, then you have an exact sequence of k vector spaces. And the finite exact sequence of k vector space, the alternating sum of the dimension is 0. So therefore, we have to have a 4. So we must have, a 3. 1 minus 4. So now what is this matrix? Now we're in the same mystery situation, right? What is this matrix? So that's some mysterious 4 by 3 matrix. But this is actually quite beautiful. Whatever this matrix is, I is generated by the 3 by 3 minors of M. I is the third exterior power of M. Right? So these are the maximal minors. The best thing that can happen to you in computation algebraic geometry is a determinantal representation. So this uncovers for us the Hilbert-Birch theorem, calculating the syzygies, gives us a determinantal representation. Okay? Today there was a new paper on the archive by Mario Como about real algebraic geometry and determinantal representation. So there is a concept, I forwarded this to you, Jan-Suk. So we've been discussing hyperbolic polynomials, and these are hyperbolic hypersurfaces. They are somewhat well understood, but much more interesting are hyperbolic varieties of higher codimension. And they have extremely interesting syzygies. New paper today, Mario Como on the archive. So here, you know, we have a determinantal representation, and this is the determinantal representation, right? That's M. So I wrote it out for you. Okay? So I wrote it out for you. So this is a 4×3 matrix whose entries are linear forms in X, Y, and Z. Okay? Now what I wrote down for you, this is what Macaulay 2 output when I did the calculation. Of course, this isn't quite unique, right? Because you can do row and column operation. You get something isomorphic. So very often, when you, as a practitioner, as an algebraic statistician, you want your determinantal representation, Macaulay 2 will give you a mess, right? So you still have to make the matrix more pretty by doing row and column operations. You get something better. But I just wrote down, you know, I mean, obviously, you know, you can do some, get rid of some, you can multiply by 39, for example, right, and get integers, so you can make these much better. But this is what outcomes, okay? Now what I wrote this in a particular form. I wrote this as X times a 4×3 matrix of scalars plus Y times a 4×3 matrix of scalars times Z plus Z times a 4×3 matrix of scalars. So we can reorganize this. We can repackage this as a 3×3×4 tensor. Right? So what I just found here is, you know, it's a matrix of linear forms, but a matrix of linear forms is a tensor. Right? So this is a 3×3×4 tensor. I can take this, pile it on this, pile it on this, right? So I get a tensor. Looks like this. Okay, now I have a tensor with 36, same 36 blocks. Okay. Now, once I have this tensor, well, I can regroup the other way as a 3×4 matrix. I can regroup this as a 3×4 matrix with linear entries in 4 variables. And the 4 variables are U1, U2, U3, and U0, U1, U2, U3. Right? So I have this tensor, but now I can, so either, you know, I started with a 4×3 matrix of linear forms in 3 variables. I wrote this as a 3×3×4 tensor, but now I can think of it as a square 3×3 matrix of linear forms in 4 variables. Well, that's a cubic surface. The determinant of this cubic is a cubic surface. Okay? And that's the cubic surface. That's called blowing up 6 points in the plane. Okay? So one of the most beautiful things in classical projective geometry is the cubic surface in 3 space, and you get it by blowing up 6 points in the plane, and in practice you do that by calculating the blue matrix and you're done. The going back the other way is a little more tricky, right? If I start with the cubic surface, so Jose walks in the door with the cubic surface, well, I can rerun this, but I have to, you know, find a determinantal representation, and that's a little more tricky. This I will not be able to do over your ground field, Jose. So if you give me a cubic surface with coefficients in Q, I need to pass to a field extension with Galois group E6. I do that by finding the 27 lines on the cubic surface. I pick 6 lines that are pairwise disjoint, and from that I get the matrix, and I run backwards. That's called blowing down. Right? So what blowing up is very easy, blowing down is a little bit more tricky. Okay? Okay, so that was number 2. So I am halfway done. I've spoken for 44 minutes, and I have 46 more. Is that true? No. That's not true. I have 20. 25. Okay, well, fine. So I have to start to erase. I have 2 more examples to go. Okay, here's example 4. Let's do n equals 9. And let's take the same example as before, but now we take the 2 by 2 minors of a 3 by 3 matrix of unknowns. Okay, so let me call the rows of my matrix x1, x2, x3 as before, y1, y2, y3 as before, but I have one more row called z1, z2, z3. Okay. Now for geometer, this describes the Segre variety, P2 times P2 in P8. Of course, in statistics, this is the independence model for 2 ternary random variables. Right? So Markov basis, the 9 2 by 2 minors of the 3 by 3 matrix. The codimension is 4, right? Because I have P2 times P2 in P8, right? The codimension is 4. Now what you do, the other thing, when you study syzygies, is you look at the so-called Betti table. And Macaulay too, in fact the classical Macaulay, came up with a wonderful format to organize these numbers. Right here we have all these numbers, right? 3, 6, 5, 9, you know. And the way we can organize these numbers is in a table. All the red numbers, all the names of the rows and the columns of all the matrices can be aggregated in a certain table. That's called the Betti table. And I'm going to give you the Betti table for this example and explain it for you. Okay? So what you do is in Macaulay 2, you go res I, that gives you the resolution, but then you go Betti. And Betti is again the last name of a mathematician. Okay? Not the first name of a girl, but the last name of a mathematician. So you go Betti res I, and it makes the following table. Okay, so 1, 0, 1, 2, 3, 4, and you go 0, 1, 2. Okay, and then in the table you see some entries, right? That looks like this. In this example, you get 1, 9, 16, 9, 1. Everything else is 0. Okay? Okay. Now this is really the resolution. So this says we have R1, R9, R16, R9, and R1. The shift downwards indicates the degree, right? So, and the degree is the sum of the rows and the columns. Okay? So this says there are 9 quadratic generators. There are 9 generators that have red degree 2. And that red 2 is 1 plus 1. There are 16 cubic syzygies, right? So this means the entries, all the entries in this 9 by 16 matrix are linear forms, right? So the columns of this matrix are labeled by 3. 1 plus 2 is 3. We have 9 quartic second syzygies, and finally one last syzygy of degree 6 over here. Okay, so this is the Betti table. So from the Betti table we see that this Cohen-Macaulay. Okay, you have to practice. This is Cohen-Macaulay, right? So Adil walks in the door, are you Cohen-Macaulay? That's a question you want to ask him. It's also Gornstein. It's Gornstein because it's a Cohen-Macaulay and it has a 1 in the lower right box. That makes it Gornstein. It's a symmetry. It goes 1, 9, 16, 9, 1. Right? That's a Gornstein situation. Okay? Now, let's try something else. Let's try to pass to the initial ideal. So here, in this example, over here, I passed to the initial ideal and I got the same Betti table. So maybe this will happen here too. Right? And maybe this will happen for Cox rings too after lunch. Maybe, maybe not. Right? But let's see what happens here. Okay? So let's pass to the lexicographic initial ideal. So let's take the lex order. So M is the initial ideal, and I take the obvious initial ideal. So x1, y2, x1, y3, blah, 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 up to y2, z3. So, h2 by 2 minor has two terms, right? It has a diagonal term and an anti-diagonal term, and just take the diagonal terms. Okay? So that's a Gröbner basis. But the resolution looks like this. Right? So you do again the Betti table. Go 0, 1, 2, 3, 4, 0, 1, 2. But now it goes 1, 9, 16, 10, 1, 2, 1, 2. Okay, that's now the Betti table. Okay. Now what do we learn from this? Well, since the 9 is the same, that says at the level of generators everything is okay. The generators form a Gröbner basis. But the Gröbner basis does not persist as we go down deeper into the syzygies. Right? As we go deeper into the syzygies, we have larger numbers. Right? It always goes up. That's called upper semi-continuity. The initial ideal always has at least as many syzygies, possibly more. In this example, they had the same number of syzygies. Here we have more, first and second syzygies. So we can see this example is still Cohn-Macaulay, because the length of the resolution is still 4. It didn't get longer, but it's not Gornstein. Right? So Cohn-Macaulay is preserved in this example, but not Gornstein property. Okay? And we can study this. And it's very interesting to study what initial ideals, preserve the resolution. Are there some ideals where all the initial ideals have the same resolution, and so on and so on. So these are active areas of study. Now, the reason I picked this particular example, because it relates in a beautiful way to a biology project that Rudy is dying to start. Let me explain. Okay? Let me first state one more theorem from commutative algebra, and that's again yellow. So here's the Egan-Reiner theorem. The Alexander dual, let's call this M. This M is the initial ideal. Okay? The so-called Alexander dual M dual has a linear resolution. Okay, well, what's the Alexander dual? Well, M here is a square-free monomial ideal. A square-free monomial ideal corresponds to a simplicial complex, also known as hypergraph to some. And there's a natural involution on simplicial complexes. Namely, what's a simplicial complex? If you look in the Boolean algebra of all subsets of an n-element set, well, a simplicial complex is an autoideal. It's a collection of subsets closed downward. Right? Well, its complement is closed upward. Now, just turn it upside down. That's called Alexander duality. Okay? So that's Alexander duality. That takes a square-free monomial ideal and makes another square-free monomial ideal, M dual. And it's an involution. Okay? Now, what does linear resolution mean? Well, linear resolution, let me draw the Betti diagram. Right? The Betti diagram looks like this: 0, 1, 2, 3, 0, 1, 2, 3. And it looks like this: 1, 6, 6, 1. Okay? Now, linear resolution means once you look at the generators, so this tells us the Alexander dual is generated by 6 cubics. 6 square-free cubic monomials. 6 cubics. But then afterwards, all the entries in the matrices are linear. There's a 6 by 6 syzygy matrix with linear entries, and there's a 6 by 1 last syzygy matrix with linear entries. Right? So linear means you start somewhere here in a single degree, and then you go over there. Okay? The Egan-Reiner theorem says for a square-free monomial ideal, an ideal is Cohn-Macaulay if and only if the Alexander dual has a linear resolution. So under this duality, under this swapping, this property of sort of staying at one level is equivalent to this being short. Okay? So whatever Alexander duality is, it sort of swaps the box. Right? It sort of does a kind of swapping operation on the Betti table. So this ideal is not Cohn-Macaulay. Because the Alexander dual is actually codimension 2. So the Alexander dual is codimension 2, but the length is 3. Okay? Now what's the connection to biology? Well, there are two. I'm going to give you two connections. So Ezra Miller is very interested in using multigraded persistence. So persistent homology. So you might know that applied algebraic topology is all the rage, right? And data analysis, in particular persistent homology. And if there's several features that you study at the same time, you get into the setting of multi-persistent homology, and then these kind of things become very important. But what I really wanted to talk about, I wanted to advertise to Rudy and Chao Chan, is a paper by Florian Bloch and Josephine Yu. Okay? This is called Tropical Convexity. The title of the paper, Tropical Convexity via cellular resolutions. And this is Journal of Algebraic Combinatorics, 2006. Okay, let me state the theorem. The main theorem. It's a short paper. They wrote this when they were students. Okay, so Josephine was a graduate student at UC Berkeley. I taught a course called Combinatorial Commutative Algebra on a book I was writing at the time. Florian Bloch was a visiting student. Okay, so this was the term paper that Josephine and Florian wrote for the course. So graduate students, please write papers, many of them soon, okay? And so this theorem says the following. So the tropical convex hull of, let's write it as a matrix. W is an M by N real matrix. But we think about this as the columns. Let's make it the rows. Let's think about the rows as M points in projective n-1 space. Okay? And of course, this is not tropical projective n-1 space. So we take the tropical convex hull of the rows in the appropriate projective space, and this is computed by the minimal free resolution. So it's supported on the resolution, on the syzygies of what? You take the initial ideal with respect to W of I, and you Alexander dualize. That's it. Okay? I is the Markov basis. I is the 2 by 2 minors of an M by N matrix. The points come in. You use the points as the weights. So x11 gets weight w11. The points define the term order. Right? So if somebody wants you to take the convex hull of M points in n-1 space, you take their coordinates and you make them the weights on the variables, x11, blah, blah, blah. And you calculate the initial ideal of I. That's this ideal with respect to those weights. Then you pass to the Alexander dual. You resolve the Alexander dual, and then the matrices in that resolution give you the tropical convex hull. Now, I am not saying this because this is the best algorithm. This is not necessarily the fast, but it's conceptually the best. It's a very good way to think about. It's one because it ties different strands of thinking about tropical convexity together. Let me just show you one picture. So the way this goes, right? Suppose you have 3 points here, here, and here. These are x, y, z, maybe, right? So if m and n are 3, we're exactly in this situation. So now somebody gives you 3 points in the plane, right? They give you this as a 3 by 3 matrix. You take that matrix as your weights. You go through all of this. You look at the matrices here. And what you see is a picture like this. All right, so there are 3 new points are created, and you get this diagram. Okay? So this diagram is the tropical convex hull. Remember that in tropical geometry, right, this is how a line looks like. So the convex hull of 2 points looks like this. Right? So this is the tropical convex hull of those points. This tropical convex hull has 6 vertices, 6 vertices, 6 edges, and 1 two-dimensional cell. Okay? This socle element here is the solid two-dimensional cell. There are 6 edges, 1, 2, 3, 4, 5, 6 edges, known as S pairs. And then there are 6 monomial generators, right? So those are 3 red given generators and 3 yellow transition, white transition generators. And then the 6 minimal S pairs are the edges. Okay? So that's tropical convexity, and that's this paper. Time is almost up, but I have 9 more minutes. So let me say one last thing. Any question? Okay, so I'm not saying I'm not saying you should do this on 1,000 points in 20-dimensional space, but this understanding the structure and understanding the math will help you, with bigger examples. Okay, last topic. So I've given you a bunch of yellow words that you should graduate from kindergarten with. So there's codimension, there's Cohn-Macaulay, Gornstein, Socle. What else do we have? We had the Hilbert-Birch theorem and things like that. And I'll give you 2 more. The first one is called the concept of regularity. And often they're again the names of 2 mathematicians, Castelnuovo and Mumford. So the so-called Castelnuovo-Mumford regularity of I is the largest degree of any syzygy. Of any syzygy of I. To be precise, you look at all the ith, so let's say jth syzygies, and you look at their degrees, the largest degree, and you subtract j. Right? So that's exactly the height of the Betti table. Okay, so that the Betti table is a box. On the one hand, we're interested in its length, right? And that is the concept of Cohn-Macaulayness. Well, we know the length is between the codimension and n, and then we want it to be short. That's a good thing, right? Castelnuovo-Mumford regularity says how far down do we have to go? And that's certainly, an upper bound. That's sort of a way to think about the generators, the complexity of the equation. That's how deep, how far down the table goes. Okay? And there's an important conjecture called the Eisenbud-Goto conjecture that says the following. The regularity of I And now there are some hypotheses on I. I don't remember exactly the hypothesis. So, I maybe is a homogeneous prime ideal, but you can get away with less. Okay? So there are some hypotheses, very mild hypotheses. The regularity of I is bounded by the degree minus the codimension plus 1. Okay? So this is one of the central open problems, I think, in this field that also Professor Kwak is very interested in. This goes back to Castelnuovo. So Castelnuovo was interested in this for curves, in particular canonical embeddings of curves. There has been progress on this, surfaces and threefolds, I think in your dissertation. There's some work on toric variety. So various cases are known, but by and large it's a big open problem. Okay? So, expert here, Si-Jung Kwak. And let's just see some examples, so just get a feeling for the conjecture. Let's look at it in our examples. Example 1, 2, 3, and 4. So the first example was, this was the box, right? So this was a child putting 36 cubes together, right? So in that case, the regularity was 8, right? So the largest syzygy had degree 11. Remember we had 11, a red 11. That was a third syzygy. 11 minus 3 is 8. The degree was 36. Well, that was the number of boxes. Okay, so this we win by a wide margin, right? Now the second example, this was the 2 by 2 minors of a 3 by 2 matrix. There it's tight, right? So there we had a degree 3, a threefold in P5, and then there it's actually tight. And then the third example, we had 3 less or equal to 6 minus 2 plus 1. This was the 6 points in the plane, right? So this is 6 points in the plane, 6 points in the plane. Again, regularity was 3 because it was generated by cubics. Again, tight. Then we had, not quite tight, I'm sorry, 6 minus is not tight, but then the next example was tight. There was the 2 by 2 minors of a 3 by 3 matrix. There's again tight. And then we had the Alexander dual of that. In the Alexander dual, we have 4 less or equal 9 minus 2 plus 1. There it's not tight. Okay, so that's a big open problem. Let me end with an important question that I think you should be aware of when you apply these things in an applied context. When you study syzygies, here's a question. Is the minimal free resolution unique? Well, it's of course not quite unique, but it's unique up to change of basis, right? This idea will always be generated by 4 cubics. Of course, I can take a linear combination. I can take 4 other cubics, but that's invariant. And those 4 cubics will always have 3 syzygies. Okay? So it's actually unique up to change of basis. Okay? There's a very, very important if. That's so important I'm going to make it red. Okay? This is unique up to change of basis if and only if I is a homogeneous ideal. What does this mean? Right? If we're in a graded situation, if we're in a homogeneous situation, then everything is okay. Now here is a very happy geometer. And this happy geometer, all he or she thinks about is projective geometry, Pn. This very happy person, let's call him Eisenbart or Lazarsfeld or Kwak. Right? This very happy projective algebraic geometer, all of his varieties on a projective space, all his ideals and modules he will ever see in his entire life are graded. So therefore, Betti numbers are well defined, Castelnuovo-Mumford regularity is well defined, and everything is unique up to change of basis. Okay? But there are some other people. Okay? Who are more, interested in, maybe applied topics. There's young me, her, right? So she's interested in, maybe she's interested in wavelets, in signal processing. Okay, so she thinks about signal processing and she wonders, can I use? In signal processing, I have seen matrices with polynomial entries, right? So I think she's at the Yonsei University, and somebody told her, maybe Hyungju Park, who is our leader next week, right? So maybe he told her that, matrices with polynomial entries is something we can study, that we can say a lot about. But there's one very, very important proviso, namely no otherwise. If we are not in a graded situation, right? If you're not in a graded ring, the number of generators is never unique, right? So if you have, for example, in one variable, take the ideal generated by x squared minus 1 and x3 minus 1, x cubed minus 1, right? This is a minimal generating set. If you throw out a generator, you make the ideal smaller, right? However, there's another minimal generating set that has only one element. Same ideal. This is minimal, that is minimal, right? So if you're in a non-generated situation, so I spoke about the PhD dissertation of Si-Jung Kwak. So let me end by mentioning the PhD dissertation of Hyungju Park. So that's centered very much around polynomial matrices, in particular the Quillen-Suslin theorem. And this theorem is not yellow because it's not part of projective algebraic geometry. So it's not on the kindergarten exit exam. But let me give you the statement anyways. It says that projective R modules are free. Projective R modules are free. So projective module is a module that looks like it's free. It's a module that wants to be free. Okay? And it's a vector bundle. So every vector bundle on an affine space can be trivialized. Okay? So a vector bundle wants to be a constant vector space. Right? It really would like to be free. It may or may not be free, but on an affine space over a field, it's always free. And for example, every submodule of R is projective. And it's free in a polynomial ring in one variable. Right? This again, so if you're in a polynomial ring in one variable, thanks to the amazing Euclidean algorithm, every submodule is not just projective, but is actually free. But you would never know this if you're in projective geometry. Okay? So projective geometry is very, very, very important. And all the concepts I talk about are for homogeneous projective situations. But there are important applications in signal processing, for example, where you have matrices with non-homogeneous entries, and then the techniques have to be modified. And I apologize for going over time.
Comment, question?
One quick question, if it's okay. Just quick. Is there any condition that equality holds, like the the bound?
Here?
Yeah.
Maybe I'll let you answer. What about the case of equality?
Yeah.
Authority.